This project builds and evaluates a text classifier on a near-balanced benchmark of AI-generated and human-written prose drawn from the Akbulut Kaggle corpus. The final model reaches 0.9984 accuracy on the held-out test. Split. That number is not the point of this talk. The point is what that accuracy conceals. Two misclassifications remain in the test set of 214 documents, and one of them carries consequences that the headline metric cannot describe. A human-written document labeled as I is not a rounding error once the tool is deployed at an institution. It is a real person facing a decision based on a model output. My aim over the next 10 minutes is to show how the model was built, to report the two errors it still makes, and to argue that a classifier this accurate still cannot stand alone as evidence of authorship. The story is the confusion matrix, not the accuracy score. The motivating concern is definitional rather than algorithmic. Detecting statistical patterns associated with AI-generated text is not the same task as proving that a particular person did not write a particular document. Detectors perform the first task. People in positions of authority sometimes treat the output as if it performed the second. That gap is where harm enters the workflow. An essay gets submitted. A detector flags it. A reviewer treats the flag as evidence, and a decision lands on a student before any closer look happens. This sequence is already in place at institutions around the world, and it rests on a misreading of what these models actually produce. 2023. Survey deployment contexts where detectors operate under exactly this kind of pressure. Sadasivan et al., 2023, argue that detection may be the ORET-I-CALI, bounded by the overlap between human and AI text distributions. My framing for the rest of this presentation follows from both papers. Benchmark behavior is not authorship proof. The corpus is the Akbulut Kaggle AI-and-Human text dataset, released under CC BY 4. After removing rows with missing values and dropping any duplicate text entries, the working sample contains 669 documents. 3069 carry an AI label, and 3000 carry a human label, which places the class balance at 50.57% I and 49.43% human. The train test split is stratified, 80-20, producing 855 training documents and 214 test documents under a fixed random seed. One structural fact about this corpus governs every result that follows. The length distribution is dramatically asymmetric between classes. AI documents average 313 characters and 44 words. Human documents average 942 characters and 271 words. That is a 6-to-1 character gap. The CSV contains text and labels and nothing else. There is no prompt metadata, no generator identifier, no timestamp, no source domain. Both limitations carry forward into the model interpretation. The method stack is in 10-channel AI shallow. A three-step ladder runs from a majority class baseline to a unigram TF-IDF logistic regression with L2 penalty, and then to a Bigram TF-IDF linear support vector classifier. All three models come from scikit-learn, Pedregosa et al., 2011. No transformer fine-tunes, no learned embeddings, no ensemble. The choice was deliberate. If a linear bag-of-words model can reach near-perfect accuracy on this benchmark, that finding is more informative than any deeper architecture would be, because it tells the reader that the signal is surface-level and lexical rather than structural or semantic. AI is the positive class throughout. So a false positive is a human document labeled as an I, and a false negative is an AI document labeled as human. That framing maps onto the error that matters most in deployment. The full pipeline runs end-to-end from the raw CSV under a fixed seed, and every step is repatterns from the exploratory analysis shape how the model results should be read. Class balance sits near 50-50, so imbalance is not a confound, and a majority vote classifier floors at 50.58% accuracy. Length asymmetry is the harder pattern. Human documents run a median of 1,871 characters and 262 words, while AI documents sit at a median of 332 characters and 47 words. Character counts across the corpus range from 51 to 4,900. That gap is large enough that a TF-IDF model could exploit length as a proxy feature and still look accurate on this benchmark without learning anything about generation style. Whether the best model is doing this cannot be disentangled without a length-matched evaluation split. Vocabulary signal is the third pattern. Top-term analysis shows concrete lexical differences. First-person markers and conversational constructions cluster on the human side, and abstract hedging with topic-specific noun groups cluster on the AI side. The signal is real vocabulary, not pure grammatical scaffolding. The Bigram, TF-IDF linear, support vector classifier is the best model in the project. On the 1/214 document test, set it reaches 0.9984, accuracy 0.9984, precision 0.9, or recall 0.99, A4 recall 0.997. One AI document is labeled as human, a false negative at a rate of 0.16% across the 614. AI test samples. One human document is labeled as a false positive at a rate of 0.17% across the 600 human test samples. The false negative is a misdetection and is recoverable by a human reviewer. The false positive is categorically different. A real person wrote that document, the classifier said otherwise, and no downstream algorithm corrects that mistake. One error, one person, potentially a misconduct flag. That single cell is why the rest of this talk argues against automated use. The three-model ladder makes the final result honest. The majority class baseline reaches 0.5058 accuracy and an AF1 of 0.678. The number looks inflated because AI is the positive class, and the model receives credit for every prediction, which is exactly why the baseline belongs on the slide. The unigram TF-IDF logistic regression lifts accuracy to 0.9835, AF1 to 0.9838, and ROCA-UC to 0.9984. Word counts alone, after standard text normalization, close most of the gap between classes. The Bigram linear SVM. RO. Most of the work comes from surface lexical signal. The SVM is not doing something categorically different. It is refining a boundary the unigram model already drew. Four limitations govern how this model should and should not be used. The length confound is the first. TF-IDF is not length invariant, and the 6-to-1 character gap between classes means the classifier may be learning that short equals AI rather than any intrinsic generation property. Nothing in this dataset can fully disentangle that. The absence of metadata is the second. Without prompt information or generator identifiers, I cannot audit whether the learned features reflect generation style or the prompt topic distribution baked into the corpus. The static snapshot problem is the third. Writing styles and generation models drift, and this benchmark has no mechanism to track that. The adversarial gap is the fourth. No document in this evaluation was deliberately modified to evade detection. Beyond those four, the ethics case is concrete. At a 10,000 student university with multiple assignments per semester, a 0.17% false positive rate produces dozens of wrongful flags each cycle. That cost does not scale with the error rate, it scales with deployment. My recommendation is narrow and deliberate. This classifier must not be used as evidence in academic misconduct proceedings. It functions as a triage signal inside a human review workflow, never as a decision. A score above a threshold should trigger a closer look by a qualified reviewer, and the reviewer should treat the score as one input alongside submission history, source context, and any other relevant information. Borderline cases should escalate rather than resolve automatically. Every prediction the model makes in a live environment should be logged with the input text, the model version, the score, the threshold in effect, and the reviewer outcome so that drift and error can be audited later. 4 research actions follow from the limitations. A length-matched evaluation. Split would disentangle length from style. Prompt metadata would enable source-specific auditing. Out-of-domain testing on news, forums, and scientific writing would probe generalization. A comparison against Detector, Mitchell et al., 2023, on borderline cases would calibrate this detector against a curvature-based alternative. 2 errors in 214 predictions is the whole story of this project. The accuracy number is 0.9984. The ROCA-UC number is essentially 1. Both are extraordinary on this benchmark, and neither changes the argument. One of the 2 errors is a human document labeled as a EI, and that single misclassification governs the deployment. The classifier works well enough to support a reviewer, and it does not work well enough to replace one. The repository holds the notebooks, the figures, the milestone drafts, and the reference list that supports every claim made in this talk, including the earlier work from Gorman et al., 2019, on GL, TR, Uchendu et al., 2020, on authorship attribution, Crothers et al., 2023, on detector deployment, and Sadasivan et al., 2023, on the theoretical limits of detection. If one image has to summarize the project, let be the confusion matrix with the single false positive cell. That cell is the reason the recommendation is triage only.